Let's continue with our discussion about truth tables and how they're applied. We ended last time with the truth table for the conditional statement, if P then Q. And we recognized that there is some sense in which this is an unintuitive notion. Okay? This stands for expressions in English like, if it rains today, then the game will be canceled. Okay? And we introduced the concept of a truth table to analyze the way this expression and the other expressions we considered behave with respect to their parts. Right? So we did a truth table for this expression, and it looked like this, P then Q. Okay? And we're defining the truth of the compound expression in terms of the parts. In the truth table, had the values T, T, F, F in the column under P, T, F, T, F here, right? And this exhausts all possible combinations of the truth values for P and Q taken together. And we recognize that if both parts of the conditional, the antecedent, which is the first part, and the consequent, which is the second part, if both parts are true, then this expression is true. If the antecedent is true and the consequent is false, then this is false. If the first part, the antecedent, is false, then we had this odd counterintuitive situation, and I gave some motivation intuitive motivation for defining the conditional as true in both those circumstances. And I said that if that is still counterintuitive to you, you can just memorize this truth table for the time being and then let those examples sit for a while until it becomes more intuitive. All right? This is the truth table for this particular expression. And what I'd like to do now is show you how it can be used to do some different things. We can categorize statements like conditional statements based on how they behave in terms of their truth values. We can compare statements, compound statements, to each other to determine whether or not they're compatible, and so on. This is one of the applications of truth tables. The other being that we can use the truth table to analyze certain arguments or inferences, and this becomes very useful. So let me give you an example of one way that a truth table is useful. Let's compare the following expressions. If P then Q, and the expression not P or Q. Okay? How do they compare in terms of their truth value? Now notice they both have the same simple statements that they're made up from, right? They both contain P and Q. It's just that in this case we use negation and disjunction to build a compound statement, and here we've used the conditional to build a compound statement. But notice this. If Q is true, then a disjunction that contains Q will also be true, right? Because we said a disjunction is true if one, the other, or both its parts are true. So if Q is true, we know that this complicated expression is also going to be true. Now, if Q is false, we know that this part is false. The only way this compound expression can be true is if the negation of P happens to be true. But on this line, P itself is true. So its negation is false. So here we have false Q and false not P. That means both parts are false. Therefore, the whole expression is false. Now, here again, on the third line, we have Q is true, and we know that guarantees this whole expression is true. And in the fourth and last line, we have Q is false, but P is also false. If P is false, then the negation of P must be true, because negation flips the truth value of the thing that it negates. Right? So here, in the last line, we also have true because this part is true. Now, I want you to take a look at the truth values in these two columns. They're identical. Now, what does that mean? Well, that means that these two expressions are equivalent logically. If they have the same truth value, given the assignments of T and F to the parts, then we say they're logically equivalent. Now, in English, of course, if we use a conditional statement or we use a disjunction, we may have a slightly different meaning. Okay? But in terms of the way these expressions behave logically, that shift in meaning in natural language doesn't matter to us. We say they're logically equivalent. They're true and false under exactly the same circumstances. All right? So we can use the truth table to develop this notion of logical equivalence. It's important you understand this because as we move into later chapters, we're going to learn about rules of implication and rules of substitution and rules of equivalence. And these will play a very important role in the concept of a proof. Okay? So remember that when you look at rules of equivalence, and they're included in the back cover of your book, rules like De Morgan's laws and commutativity and associativity and so on, that you're allowed to substitute in one expression for another expression in an argument or in a proof only when they're equivalent. All right? So our sense of logical equivalence comes down to the concept of a truth table and this idea of having exactly the same truth value. All right? So these expressions are equivalent. If P, then Q, not P or Q. Now, we can also analyze certain expressions like, let me do a different truth table here, a simple one. Let's look at the expression P or not P. Okay? Here's an expression. We may be interested in analyzing its structure, determining when it's true and when it's false based on the true and false for P. Now look at this. If P is true, here's a disjunction, right? P or not P. And we know this is an inclusive or. If P is true, then one of the parts of this disjunction is true, and so this is true. If P is false, this part is false, but notice that the negation of P is true, right? So in this condition, the other part of the disjunct is true, and so the whole thing is true. So for the truth table for this expression, P or not P, you get true for every value of true or false for the parts. Right? So it's always true. It's called a logically true expression, and the term for this is a tautology. All right? So you start to see now how we can use truth tables to classify certain expressions. If I say something is a tautology, you now know what that means. It means no matter what the parts, no matter the truth values for the parts of the expression, that expression is always true. For example, if I say to you, either it's raining outside right now or it's not raining, you don't have to go outside to determine whether or not that statement is true. You know that one or the other condition holds. All right? Logically true expressions are of that type, and we can use truth tables to classify them in that way. All right, let's look at the concept of a self-contradictory expression. If I am looking at the simple truth table for, whoops, this isn't going to work. Here, is it? Well, maybe it will. Okay. I have P, and then I have the expression P and not P. Okay. Now I know that P can only be true or false. Those are the only possibilities. How does this behave based on the behavior of its parts? Well, if P is true, then part of this conjunction is true as well. But the other part is false. Now we know that a conjunction is true in exactly one circumstance, and that is when both its parts are true, right? So here, if P is true, one of the parts is false. And if P is false, one of the parts is false. So here we have an expression that has a truth value of F, it's false, for every possible combination of truth values of the parts. Right? This is what we call a self-contradictory statement. It can never be true. If I say it's raining and it's not raining outside right now, you know there's something wrong with the statement I've just made. Okay? Something wrong with me. All right, so this is a self-contradictory statement, and we use the truth table to capture this idea of categorizing expressions in this way. So that's one application of the truth table. Now, a more interesting, more useful application of the truth table is the following. We can see not only how specific statements behave relative to their parts, we can see how statements behave taken together in combination. Okay, so let's take a look at an argument form. A particular argument in English. We'll start with that. If it rains, the game is canceled. It rains. Okay. If these two statements are taken together, then you know something else follows, right? What follows? Well, the game is canceled. Now, this represents an argument form, or is an instance of an argument form we call modus ponens. If P, then Q, P, therefore Q. This is more than just a single statement analyzed on a truth table, but we can develop truth tables that allow us to analyze the argument itself and literally show us why it is this is a valid argument form. So let's do that on this board. Okay. The conditional, if P then Q, is made up of two parts, and we've seen this truth table before. True, true, false, false, true, false, true, false. Okay. And we know how this plays out. If P then Q is true, false, true, true. Now, instead of looking at this truth table simply as a truth table for the statement if P then Q, we can reinterpret it as a truth table for the argument called modus ponens, right? Because modus ponens is an argument that takes this as a premise, the conditional, if P then Q is a premise, and it takes P as an additional premise. And Q is the conclusion of the argument. Now, what we're interested in doing here is answering the question, is this a valid argument form? Okay, this allows us to see if this is valid or invalid. And as I said, intuitively, you know it's valid. All right. But to go back to our discussion of validity some sessions ago, remember that an argument is valid if the following is the case. If the premises are true, then the conclusion must be true. Now, the truth table shows us all possible combinations of true and false for complex expressions like this. Now, since this is a premise, and this is a premise, and this is the conclusion in the argument called modus ponens, we can check the truth table to see exactly when the premises are true. Well, look, this premise, if P then Q, in this argument is true here, and the other premise, the second premise, is also true in this line. Here's the conclusion in that line. Is it true or false? It's true, right? So here we see that if both premises are true, then the conclusion is true also. Is there any other case where both premises are true in this table? Well, here you have a value of f for if P then Q, so clearly the premises if P then Q and P taken together wouldn't both be true, right? Here f is false even though the conditional is true. Right? The only line in this truth table where you have true premise and true premise is on the first line. So what does this mean? You look at this truth table and you say, okay, I see on the only line where the premises are true, the conclusion is also true. That means there is no single line in this truth table where the premises are true and the conclusion is false. That literally shows us that this is a valid argument form, right? If in a truth table, let's say, let me just deal in the abstract for the moment. Let's say we have premises x, y, and z, and we're looking at a conclusion, w, and we're asking the question, does this follow from these premises? If you ever find a line in the truth table where you have true, 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 false, you know that the argument is invalid. Okay? When we look at a truth table that represents an argument, what are we looking for? We're testing every line where the premises are represented as true all at once, and looking over at the conclusion column and saying, okay, is the conclusion true or false? If there is one line, right, there could be 100 lines in the truth table. If there's one line where you get true premise, true premise, true premise, false conclusion, then we say the argument is invalid. We don't say, as sometimes students do, well, the argument is invalid on that line. No, no, no. It's an all or nothing thing. Either the argument is valid or it's invalid. And if you find one line in a truth table where the argument has true, true premises, false conclusion, then the whole thing is invalid. All right, let's take a look at an example quickly that illustrates an invalid argument form and how that's represented in the truth table. So you'll have a point of contrast. I'll erase this just so we can start fresh. Okay, there's another argument form. This is called a logical fallacy. If P then Q, not P, therefore not Q. Now this is invalid. Okay, think about it in terms of the English example I gave earlier regarding the game being canceled. If it rains, then the game is canceled. Well, it doesn't rain, so the game is not canceled. Does it follow the game is not canceled just because it doesn't rain? No. There could be other reasons that the game is canceled, right? Maybe the coach had a heart attack, or maybe there's a bomb threat, or whatever the case may be. The game still could be canceled even though it doesn't rain. So the conclusion here intuitively does not follow from the premises. Now we can see that literally on the truth table for this argument. Again, we have P and Q as the parts. If P, then Q is the conditional. And we have to add a few extra things here. Not P and not Q. Okay? I have to extend this a little bit. All right. So we know how the truth values can be combined for P and Q. True, whoops. True, true. True, false. False, true. False, false. We know already from seeing this a dozen times that you have true, false, true, true for the conditional. Now, how does the negation of each of these parts behave? Well, when P is true, this is going to be false. It's going to be false. It's going to be true. Going to be true, right? It simply flips the truth value of P in that first column. And then here we have false, true, false, true. Okay? Now, label the columns in your diagram, in your truth table here. It's premises, conclusion. We know that this is a premise. We know that this is a premise. We know that this is the conclusion. Okay? So, this truth table represents the information about the possible combinations of truth values for the parts of the argument. Okay? Here we have a true premise, but this is also a premise and it's false. So this isn't a line that's terribly interesting to us because we're just looking for those lines where all the premises come out true. Those are our test case lines. Right? Is there a line where the premises are both true? Well, yes, there is. It's the third line. Okay? And so we look at the premise, and both of them are true in this particular scenario. And here, the conclusion is false, right? Now here you have a line where the premises are true and the conclusion is true also. And this may be confusing to you. You say, well, wait a second. Well, is the argument valid or invalid? Remember what I said. All that it takes to show that an argument form is invalid is if you find one line in this list where you have true, true, and false. That's good enough to show that the argument is invalid once and for always. All right? So, let me recap. really what we're doing here is we're using this tool of the truth table to apply to arguments and to statements. We classify statements depending on how they behave. Are all the entries true for a particular statement? If yes, we call it a tautology. If they're all false, we call it self-contradictory, and so on. But now we're applying it to arguments, and the truth table allows us to see literally how the argument behaves, what the relationship is between the premises and the conclusion. And if the argument is valid, we'll see it. How will we see it? We will not be able to find a single line in the truth table where the premises are true and the conclusion is false. If we find such a line, we know the argument is invalid. Now, you can apply this to all sorts of argument types, and you do in the exercises, and the textbook provides lots of examples. The point I want to make in closing is this. This is a useful conceptual tool for understanding how compound statements behave based on their parts, right? How you determine the truth value of a complex expression based on how it's put together and the truth value of its components. It's useful for understanding that. It's useful for understanding this concept of validity because we really start to see here what it means to say, well, if the premises are true, then the conclusion must be true also. The drawback of this method is that if you have a large number of statement letters in your argument, then the truth table gets very large very fast. In fact, the number of lines increases exponentially. Okay? The number of lines in a truth table is equal to 2 to the nth, where n is the number of statement letters. We've been looking at very simple arguments that have 2 statement letters, so there are 4 lines, right? 2 squared is 4. What happens if you have 3 statement letters? Well, then you have 8 lines. You've doubled the length of your truth table. What happens if you have 4? Well, then you have 16 lines. So all of a sudden, this very useful conceptual tool becomes a little unwieldy, right? If you have arguments that have any real complexity to them, you might have a 4-page truth table where you're trying to analyze the argument. Okay? Now, in principle, you can do that, but in practice, it takes too much time. So, what do? What we want to do is we shift away from a discussion about truth tables to a discussion about proof in our next session. Is we want to take the insights we've gained from truth tables and analyzing little arguments like modus ponens. And we want to turn these insights into what we call rules of implication. We want to develop a new method based on the concepts here that it isn't nearly as cumbersome. And that's really what proof is all about. Okay, we're still interested in this question, do the premises imply the conclusion? Is an argument valid? But we don't want to have to resort to this particular unwieldy tool in order to analyze real arguments of real complexity. So that's where we'll move into this concept of proof in Chapter 7.